We've all seen these huge AI models, right, running in giant data centers. But what if some really surprising stuff is actually happening closer to home, like right on the devices we use every day? Today, in this deep dive, we're going to unpack a really fascinating example of exactly that.
Yeah, we're zeroing in on Google's new model, Gemma 3 270M. And the whole idea behind it is hyper-efficient local AI. That local part is honestly pretty revolutionary. It means you can have powerful AI running directly on your device.
Which means things like more speed, better privacy.
Yeah, sure.
No constant back and forth with the cloud.
Exactly. It really changes where powerful AI can actually, live and operate.
Okay, so our mission today is to figure out the how. How does this relatively compact model get fine-tuned to master something complex like chess?
Yeah.
Like predicting the next move. We'll trace the journey, looking at the sources, from loading it up to seeing what it can actually do. It's all about understanding the mechanics behind this kind of specialized AI.
Yeah.
Right, let's unpack this then. Gemma 3 270M, hyper-efficient local AI. What does that actually mean in practice, beyond the buzzword?
Well, it's really about the design. It's built from the ground up to give you the most performance for the least amount of power, basically, optimized for edge devices. So you get real-time processing, less lag, no need to constantly send data out. The first step, naturally, is getting the model itself loaded up, that and its tokenizer.
Okay.
And a key tool here is something called Unsloth AI. It's crucial because it's specifically designed to make fine-tuning way more efficient. Cuts down memory use, speeds up training time, especially for models like Gemma.
Right. Efficiency is the name of the game here. So to get Gemma 3 from being just a general model to being extremely smart at playing chess, we need fine-tuning. This is where it gets really interesting, I think. You mentioned LORA using Unsloth's PFT. How does that make fine-tuning so efficient? We're not retraining the whole thing, are we?
No, definitely not. That's the beauty of LORA low-rank adaptation. It avoids the massive cost of changing every single parameter. Instead, with Unsloth's PFT, that's parameter-efficient fine-tuning, you're essentially adding these small, trainable adapter layers on top.
Like little specialists.
Kind of, yeah. Think of it like adding a very specific chapter appendix, not rewriting the whole book. You specify the model, then this R value, the rank, which controls the complexity of these adapters.
Okay, so R is like a dial for how complex the new learning is.
Pretty much. Higher R captures more detail, maybe costs a tiny bit more efficiency. Lower R keeps it super lean. And you also pick target modules, specific layers inside Gemma to attach these adapters to.
So you're focusing the learning surgically.
Exactly. It's about hitting that sweet spot. Game the chess skill without wrecking the efficiency Gemma was built for.
Makes sense, a targeted approach. But even with smart adapters, you need the right teaching material, the right data. What are we feeding this model to make it a chess whiz?
Right. The data comes from the Chess Instruct dataset. You can find it on Hugging Face. And it's not just random games. It's structured. You get a sequence of chess moves, but crucially, one move is missing. And you also get the final outcome of the game. So the model's job is clear to figure out that missing move based on the context.
So it's learning strategy and tactics by filling in the blanks.
Precisely. It's learning the patterns, the why behind moves by predicting what should have been there. It builds that predictive power.
Okay, so you have the specialized chess data. But how do you prep it? You can't just feed raw chess notation into a language model, can you? It wouldn't understand.
No, you're right. That's where the standardized data formats method comes in. It's absolutely vital. Think about it. These models are trained on, well, conversation, right? Text that flows like human language.
Yeah.
So throwing raw chess notation E4, E5, and F3 at it is like trying to teach, linguistics using only math equations. It doesn't fit. This method converts the chess data into more of a conversation style, like maybe user. Given this board state, what's the missing move? And assistant. The move is NF3.
Oh, okay. So you're translating the chess problem into the model's native language.
Exactly. It makes the data digestible, yes, but more importantly, it makes the fine-tuning process much, much more effective.
Got it. So data prepped, model ready. Before we actually start the training, there's this trainer object you mentioned, setting up the command center. What goes into configuring that? It sounds important.
Oh, it is. It's the blueprint for the whole learning process. It's where you set things like the learning rate, how quickly the model adjusts its knowledge, but also things like batch size, how many chess examples it looks at before updating itself, and the number of epochs, how many full passes through the entire data set.
So tuning those settings is key.
Definitely. It's a bit of an art, finding the right balance. Get it wrong, and training might be slow or it might not learn effectively. It's where you make the strategic choices for the training itself.
Right. Okay, so setup complete, strategy decided. We hit go on training. You mentioned seeing the loss generally decreasing with steps. What does that actually signal when you see it happening?
That decreasing loss is basically the model telling us I'm getting it. It means the model's predictions about the missing chess moves are getting better and better over time.
It's learning.
Yes, it's successfully internalizing the patterns from the chess instruct data. Its errors are going down, its accuracy is going up, it's becoming more confident and correct in its chess predictions.
Which leads us to the payoff, right?
Yeah.
The before and after.
Absolutely. This is the aha moment. Before fine-tuning, if you ask the base Gemma 3270M model about a chess position, it would just generate random stuff. Often illegal moves, total nonsense.
Like asking a baby about chess strategy.
Pretty much. But after this focused fine-tuning, it's remarkable. It can pinpoint the exact missing move from the sequence. It's not guessing anymore, it's making an informed prediction based on what it learned. The precision it gains is really quite fascinating.
So think about that for a second. You go from complete randomness, total guesswork, to predicting the single correct chess move. That's a massive jump. But the real story here isn't just about making an AI good at chess, is it?
Not at all.
It's proof that really powerful specialized AI doesn't always need a giant server farm. It can be trained precisely and run right there on your device.
Yeah, it sort of democratizes access to this kind of specific intelligence, opens up doors for custom AI solutions we maybe couldn't even imagine before.
So we've really seen quite a journey today. Started with a general, efficient AI model, Gemma 3270M, and watched it become a specialized chess predictor through this targeted local fine-tuning.
And stepping back, looking at the bigger picture, this kind of thing really changes how we should think about where AI happens. It underlines the huge potential, maybe still mostly untapped, of these super efficient local models. It's not just about games. Imagine specialized AI assistants for coding, for writing, for analysis, all running locally, tailored just for you. It shifts capability away from just the big cloud providers.
Absolutely. Which leaves us with a really interesting thought, doesn't it? If we can train an AI so precisely to master chess right on our own devices, what other incredibly specific, super efficient AI skills could we develop? What happens when intelligence gets truly personal and local, turning our everyday gadgets into bespoke experts for, well, almost anything?